So our last talk of today, I'm sure you're all very excited to hear Kevin Mitchell talk. So just a few words about Kevin. Kevin is Associate Professor of Genetics and Neuroscience at Trinity College Dublin. He studies how genetic programs wire the brain and how development yields individual variability, I think. In recent years, and a big part of the reason Kevin was one of the first people actually that came to mind when we thematized our conference here. As many of you probably know, Kevin has been branching into more philosophical territory and exploring how the insights of genetics and neuroscience bear on questions of agency and free will, and I think been doing a very good and interesting job of that. He's the author of two popular books, Innate and Free Agents, How Evolution Gave Us Free Will, the latter of which offers a biologically grounded account of choice and control across evolution. And just as a bit of a personal aside, Kevin was maybe one of the first speakers I ever engaged with in organizing a conference. When we organized a conference, me and Abiba Bahrain, about 12, 15 years ago, and Kevin was kind enough to come and speak at that conference and give us insights about how to write well, and he's since gone on to do that very well. So delighted to have you here, Kevin, and looking forward to your talk. Take it away.
Oh, thanks so much, Mark. Thanks, Tom. Thanks to all the organizers. I'm really sorry I couldn't be there in person. I'm afraid it's my sort of heavy teaching load right at the moment. So, but I'm delighted to be able to join virtually, as it were, and I'm going to give a really kind of a broad, zoomed out overview of some things I've been thinking about in terms of agency, in particular, chance, choice, and control. So the big question really, I think, in a metaphysical sense, is to ask, how can an agent be in control? How can it be a right way of talking to say that an agent does things, an organism does things, as opposed to just stuff is happening, right? So how can the organism as a holistic entity really have any causal powers unto itself? And the counter to this, which I think is really endemic in our thinking, actually, is that everything just comes down to physics. And so there doesn't, it can seem like a convenient way of talking to talk about agents doing things, but really all the causal work is just physics playing out. And that kind of view is pervasive in the free will literature. In fact, the free will literature is often just taken to be a debate where free will is set against determinism, where determinism is defined as something like this: the thesis that facts about the remote past, in conjunction with laws of nature, entail that there is only one unique future. So this is endorsed by Greg Caruso and Dan Dennett in a recent book. And they both agree with this premise, but they end up with different sort of interpretations of what that means, either between free will skepticism or compatibilism. But the premise itself is not questioned, which is odd, because the premise has some pretty stark implications. So the idea, another way to phrase physical determinism, is that the state of a system at time t, exhaustively defined, plus the laws of physics, just necessitate the state of the system at time t+1. Right? Now, if that were true, then everything that has happened since the Big Bang to me saying this sentence would have been already predetermined at the Big Bang. That seems like a fairly absurd claim on its face, actually, and turns out there isn't really any good evidence for it. The problem, of course, for free will, if determinism is true, at least according to the skeptics, though not the compatibilists, is that, first of all, there are no possibilities. There's just one inevitable timeline. So for an agent or an organism, it can have no choices in the sense of options. There's just no options available to it. So it can't exercise choice. There aren't any doings in that world. There's just things happening. And in fact, there's not really even a coherent notion of causality, because normally when we think about causality, it entails that something else might have happened, that there was some difference maker we think about in terms of counterfactual logic and propositions. Of course, that's the debate around free will in humans, but there's equally a problem for any kind of agency, right? For any organism to be able to do anything, it has to be a locus of causal power. Now, how could that be if physical predeterminism is true? Because physical predeterminism, based on those laws of things like quantum mechanics or other elements of physical theory, implies causal reductionism. And this is actually the hidden sort of real problem of determinism. It's not just that things are going to play out, it's that all the causes are exclusively bottom up. We've got causation by parts, not the whole entity. So how can we get beyond that? Well, the first thing to do is to ask whether determinism actually holds. And this is a paper that is under review at Synthese at the moment. It's by myself and my graduate student, Henry Potter, and George Ellis, who's a very eminent physicist. And basically, we look at the evidence for determinism and find that there isn't any evidence for determinism in physics. And I want to go through some of that because it's not just that we can say the universe is indeterministic, it's indeterministic in a certain way, which isn't the way that many people have thought about it. At least that's our conclusion. So here was our way of defining what determinism looks like, and we can ask whether that holds. And in fact, it doesn't, because first of all, the state of the system at time t, it's impossible to define the state of a system with infinite precision. That just doesn't, that's just a physical impossibility. And secondly, the equations that govern how the system evolves are also not actually deterministic. They're probabilistic, really inherently probabilistic. And we know this from quantum mechanics, where, for example, the Heisenberg uncertainty principle just shows that particles can't simultaneously have infinitely precise values of things like position and momentum, not because of anything to do with observers and their certainty. That's just to do with the physics of the system itself. And then the Schrodinger equation, which describes how quantum systems evolve, how the wave function evolves through time, is deterministic in itself until something happens. And then it's not deterministic because it's only giving a description of probability density functions through time. So it doesn't actually predict the outcome of specific experiments or just in general of any interactions that cause a resolution of the probability density function. Some single actuality will arise. It's based on those probabilities, so it's constrained, but it doesn't depend on an observer. And what happens is actually really, really just probabilistic. There's lots of ways that people have tried to rescue determinacy in quantum mechanics, which none of which have worked. There's ideas of hidden local variables where people say, okay, well, it looks probabilistic to us. It's just because we don't know that there's some other stuff there that is actually determining the outcome. And there's very good evidence and theory that not only that isn't the case, but that it couldn't be the case. And then there's things like the multiple worlds hypothesis, which just says, well, actually everything happens when the Schrodinger equation has some sort of a collapse of the wave function. In fact, all of the probabilities happen, and each one generates a new universe where things carry along there. Now, if that were true, then as I've been talking, an infinite number of universes would already have been created, which we could know nothing about. So it's a really metaphysically extravagant kind of hypothesis that just doesn't really do any work because it's not explaining what's happening on the timeline that you're actually on right now. And in fact, pretty much everyone accepts that quantum physics is indeterministic, and yet they will also say, yeah, but okay, but classical physics is deterministic. And there's a few sort of arguments that people make for why that should be the case. And we call them Las Vegas arguments because it's sort of like what happens in the quantum realm stays in the quantum realm. Some of them are based on real physical, detailed physical theory from quantum mechanics, like issues of quantum decoherence, where the idea is that at small things are quantum, and at some point they get big enough or entangled enough that they lose their quantum properties. And that's really sort of misunderstood. What that means is that you don't see things like superpositions of cats, right? So large classical scale objects don't have weird quantum behavior unto themselves, but they still have weird quantum behavior inside them. There's still quantum stuff going on inside them. There's still wave functions forming and collapsing in a probabilistic nature all the time. So this doesn't get rid of what's called the measurement problem of this idea of indeterminacy. That's still there at the lowest levels of these classical systems. But even if it weren't, due to quantum stuff, the classical systems have their own measurement problem, because this still holds. It's impossible to find the state of a system with infinite precision, and it holds for a different reason, which is that information is physical, right? And there's a limit to how much physical information you can store in any quantity of space. It has to have a certain energy. If you exceed that limit, which is called the Bekenstein bound, then you'll basically cause a black hole. So you can't store infinite information in some finite amount of space, which means that the idea that the amount of space at the Big Bang stored all the information about everything that happened since, including what I'm saying right now, just becomes a mathematical impossibility as well as a ludicrous sort of situation, especially because the universe is expanding and information is increasing. So it's not just the possibility space is expanding. So the universe may have started in a situation with low entropy, and it's increasing. The maximum possible entropy is increasing as the universe expands, but the actual entropy is increasing at a lower rate. So Arthur Eddington described that this way, that the expansion of the universe creates new possibilities of distribution faster than the atoms can work through them. And what that means is that you've got an increase in information as time goes on. So there's an idea some people refer to in quantum mechanics of conservation of information, which just is wrong. It doesn't apply and to the real world where things are actually happening. Now, another sort of Las Vegas argument is just to say, but we know classical physics is deterministic. You know, Newton's laws and all those things. There's no probabilistic nature to them. Well, it turns out it just isn't deterministic. That never has been a result of physics. It's an idealization. It's an assumption that physicists make for convenience, basically. So Newton's mechanics seem deterministic, but only under a number of idealizations, some of which are given here. And in fact, even Newton himself realized that for the solar system, which is a highly simplified system, even there, what he called irreducible irregularities will at some point make all of the predictions of where things will go untenable, basically. So that kind of imprecision matters for most systems. If the parameters of the system can't be defined with infinite precision, then when you apply them to the equations, multiple things could happen. Now, for systems with simple linear dynamics, like the orbits of the planets, those imprecisions remain small until you get out to 200 million years or something like that. But for systems with complex nonlinear dynamics, those imprecisions can be amplified over time. And we know that that's the case from studies of chaotic systems, for example, as documented by Lorenz and others, where he had, in this case, it was a computer system running a simulation of what the weather would be like over time, given some set of parameters here. And what he found was that if he truncated the parameters and ran it again, then on the second run, he would see this divergence over time, where ultimately they would be so far apart from each other on these different runs that they were effectively not related to anything that was happening here. They were as random as they could be. This is often sort of misunderstood, I think. So people will say, but chaotic systems are deterministic. And in this case, it is deterministic. The only reason these diverged is because he went back and ran it again and changed the numbers, right? So he truncated the numbers after the decimal point from like 8 decimal points to 4 decimal points, and then something happened. If he left it alone and ran it again, he would have gotten exactly the same result. So the simulations here are deterministic. You have to do something to it in order to get a different outcome. But that's just the computer simulations of the chaotic system, which are deterministic because they're made to be deterministic. That's people go to a lot of effort to make computers work in a deterministic fashion. But if the real system is characterized by finite precision of physical parameters all the time, which we call pervasive indefiniteness, then the openness of future states is is ontic. That means it's genuinely existing. It's not just anything to do with what we can know. It's not merely epistemic. And that's a view that we call pervasive indefiniteness. And it's really importantly different from a view that where most of the time things are proceeding in a deterministic fashion. It's just occasionally you get this little sprinkling of randomness that pushes things one way or another. So if it interrupts the normally deterministic go of things by these little burps of randomness that come into the universe from somewhere, that doesn't seem to be the picture that is realistic, where the randomness is some positive thing that's injected into the world. Instead, it's an underdetermination, right? It's a negative. It's not a positive. There's this underdetermination of the future by the present state plus the laws of physics. That becomes really important because the underdetermination is the thing that gives a little elbow room for some other kinds of causation to come into play. So there's a few ways of thinking about this. Under determinism, we have this sort of a sacred timeline. Just one thing could ever happen. In fact, there shouldn't even be past and future on this thing here because there's no direction of time in a deterministic world. In determinism plus randomness, which is the way that we think a lot of people in the literature have thought about it, you have this sort of thing where, okay, things are deterministic generally, except occasionally there's a random bump which could push it one way or the other. So each of these little forks in this garden of forking paths is the intrusion of some positive randomness into an otherwise deterministic flow of things. And we don't think that that's an accurate way of describing things, and it gets it means it puts people in the wrong frame of mind when thinking about agency. If you think in this way, this kind of a pervasive indefiniteness, this underdetermination, then the future is just open. And it's not wide open. It's not that anything could happen. There's a possibility space, and that could be more or less constrained. And over time, as that possibility space goes along, you get this expansion of possibilities into the future, such that beyond some point, the future state of the system just doesn't have a truth value. It's just not the case that we can say whether it will be raining a year from now or not. There's a yes or no answer to that we just don't know. That's not right. There just isn't yet a yes or no answer to it. The system has to evolve through time to resolve that indeterminacy. Now, one important factor is that this is what would happen if the system is allowed to evolve under only local rules. So if those low-level laws of physics are the only dynamics that are at play, then things could go in the far distant future in all kinds of directions. Importantly, that's not the way a lot of the systems that we're interested in actually work, especially living organisms, because they have global rules that constrain how things can go. Okay, so how does this work? Well, in the free will debate, and it's pretty much the same for agency, you could say under the premise of determinism, we have to ask where could the freedom come from? But under indeterminacy, we don't have to ask that. The freedom comes for free. The future is radically open, or at least it's open enough. Now the question, though, is where does the control come from? Because we don't want to have a situation where what happens is just determined by the randomness, then the agents wouldn't be in control either. So how does the organism make happen what it wants to happen out of this possibility space? And the answer, we think, was really already hit upon by Epicurus thousands of years ago, where he argued that a little bit of randomness creates this sort of causal slack. So he said it was loosening the treaties of fate so that macroscopic organization can have a causal influence. And in fact, he argued that that's the only reason why we get macroscopic organization in the first place. That if we didn't have that kind of randomness, we wouldn't have agents to talk about whether they have free will or not. That idea has been also put forward by George Ellis and Helen Stewart and others, this idea that you get macroscopic organization that influences the way that things go. Alicia Huerero has talked about this and written about it really nicely. So in terms of constraints. So the typical sort of Newtonian way of thinking about things that I think we're all inculcated with in our scientific education is that physical forces are the real causes. So things pushing into each other are the real causes. And the idea of constraints as being causes doesn't seem quite right. But actually, that possibility space can be constrained. It's just what physicists call initial conditions or boundary conditions. And those constraints, it's not just that they reduce the possibility space, they create new possibility spaces. They can be enabling. So constraining lower level parts enables higher level functions. Just like looking at this computer here, the way that this is set up, the way the hardware is set up, and the way the software is running constrains how the electrons are flowing within it for a purpose, right? It's for the purpose of running this program where I can talk to you on the other side of the world right now. There's nothing magical about that. It doesn't violate the laws of physics. Electrons still behave like electrons. It's just that their possibilities are constrained by the physical organization, but actually importantly, also by the abstract nature of the program that they're running, right? There's an idea in somebody's mind that's been formalized into machine code, but it has effects on concrete systems. So yeah, like I said, the typical way of thinking about causation is this idea of production causes. So we could say the balls here will scatter apart because the cue ball hits them, right? So the cue ball is supplying a force. You can measure that in terms of physics. You can work out the momentum and all that kind of stuff. But that's really only half of the picture because there's also dependence causes. If we want to explain why the event happened the way that it happened, then we have to take into account the materials that things are made out of, the organization of the balls here. If you've ever had somebody give you a loose rack when you're braking in pool, it's very disappointing, right? So that's a dependence cause. You supplied the same force, but the same outcome didn't happen. So dependence causes can be really generic, just like the laws of physics happen to hold. Gravity has a certain strength, chemistry of carbon or whatever, those things are what they are. That has an effect. But they can also be more local. They can be more interesting, and they can have functional importance. And that's especially true for systems like living systems, which have historicity, right? They carry their history in their structure. So structuring causes, which is another sort of term for this, become crucial in understanding what life is. You can't just take a synchronic view of living things right at a given moment and understand them as having a physical state. They have a history, and that's what we need to understand in terms of their causation. So we need a diachronic view of causation. Now, importantly, thinking about these dependence causes through time, what we have to think about is that it's not just that you get some macroscopic organization and it affects things. It's that the macroscopic organizations that we see may have been selected for, and for for some kind of reason, some functionality, and for living things. In fact, for everything, the things that we see are the things that persist, right? So every sort of thing is selected, not in an evolutionary sense, just in a physical sense, for stability. But living things are selected for persistence through time. And that, I think, is a key sort of way of thinking about living systems and living agents. And Schrödinger talked about this in his What is Life book, where he took a physicist's view to explaining why living organisms are these patterns of organization that can resist the second law of thermodynamics and just becoming one with the universe, right? Going to equilibrium. So we can say that in a world where many things could happen, organisms do work to make themselves happen. That's the first thing that they do. It's the first thing that they cause. They cause themselves through time. And Immanuel Kant had a really, I think, insightful view of this, the idea that a definition of an organic body is that it's a body, every part of which is there for the sake of the other, reciprocally as end and at the same time as means. And what that means is there's this sort of whole part regime that is constraining the parts, but it's also generated by the parts. And Stuart Kauffman has sort of followed up on that idea. Now, that may seem a little bit metaphysically problematic, right? Where we have this arrangement comes from the parts and what they're doing, but then at the same time, it's supposed to impose some sort of power or causation top down. And the problem, I think, again, has to do with the way that we think of time, right? So if you think of time just in terms of these instantaneous states and causation at that time, then it's going to look weird, right? Then it's going to look like circular causation. But actually, if you tilt this thing, then what you realize you're looking at it end on. It's actually a spiral. So you get this spiral causation as time goes on, where global effects are interacting with local effects, which feed back to global effects, and so on. So that you don't have this sort of metaphysical conundrum that many people seem to think is at play here. Okay, so we can think of organisms then as self-stabilizing processes. They just are systems or regimes of constraints. But here's an important factor that I really want to emphasize is that they're macroscopic regimes. They're not trying to constrain all their little bits all the time. Those bits are super noisy, right? At a microscopic level, all kinds of noisy stuff is happening, but at a coarse-grained level, the overall pattern is constrained. So they don't have the need to control these, and they don't have the power to control what's happening at individual, quantum fluctuations and stuff like that within them. They just need to constrain what happens at the macroscopic scale. So I want to emphasize, I guess, how radical of a thing this is, right? So there's an idea, people talk about emergence. It's a very muddy kind of a term, but people think, okay, yeah, you can get new properties at a higher scale when you organize certain things. Maybe there's some principles that you get at play that aren't derivable from more fundamental laws, but given the state of a system at any time, you can still sort of explain what's happening at the macroscopic level. But I think I want to go actually further than that and say that selves organisms are transcendent. They transcend the low-level causation. They escape from that to a certain degree. They have new causal powers as holistic entities that constrain the goings-on at lower levels. Without violating the laws of physics, it's just a new type of causation on top of that lower type. Okay, the problem with that the organisms face, of course, in trying to keep making themselves happen is that the world is not cooperating, right? Things are changing out in the world, and living organisms then need to know what's out in the world and what should I do about it in order to be able to persist in this dynamic situation. So they have evolved systems of sentience, so they have sensory systems, and systems of agency, so they have control systems that allow them to control, well, to change what they're doing and to change what's happening. But the what should I do bit is the really crucial bit, because you need to connect those two in an adaptive way, right? You need to have the thing that you're doing be appropriate for whatever is happening out in the world, which means you need some knowledge, right? You need to know what to do, and that requires some learning systems. And the first learning system is evolution itself, which can just pack in a lot of control policies into living organisms that allow them to do appropriate actions under given conditions. But then, of course, evolution hit upon the idea that it could equip individuals with their own onboard learning system, which allows them to, in their own lifetime, accumulate more experience about adaptive behavior. So if we think about even like simple things like bacteria, then, so here's a little bacterium. It's got its internal metabolism. It wants to keep this going. Things are changing out in the world. So it has a purpose here for staying alive. Nothing else had a purpose before living things came along, but once they're there, this is real, right? This idea that we should be allergic to teleology is sort of odd. I mean, I think we should be allergic to cosmic teleology, but once living things arise, it's perfectly reasonable to say that they're trying to stay alive, even if we just cash that out in thermodynamic terms, I think. So here's our little organism. It's trying to stay alive. Things are changing. Maybe it's using up food. Maybe it needs to find some more food. So it needs some sensors that give an internal signal. And the causation here is really different from physical causation. It's not, nothing's being pushed here. There's no transfer of matter or energy. There's just a conformational change, really an informational change here that signals something about things happening in the world. And that has value and it has meaning. The meaning here is just pragmatically approach or avoid. Those things can be wired in as control policies. So here you can have a simple thing where there's like a signal, do an action. If A, do X. And you could say that those embody a pragmatic knowledge about the world that's wired in by evolution. Now the problem with that is it seems very reductive, right? It doesn't seem like the organism's doing anything. It just seems really, really kind of linear. In fact, it's not so linear. There's a bunch of other stuff that can be happening. Usually there's some contextual control, even in these sorts of simple organisms, where you could say, actually, what's happening is that a situation is being assessed. It's not really responding to isolated stimuli. But there's a tendency, I think, in biochemistry and cell biology to try and work out specific pathways that are involved in specific behavioral events. So here, for example, we got our little bacterium. It's detecting something with a receptor. You've got some signal transduction pathway inside it. It eventually impinges on the flagellum and determines which way the bacterium goes. And if you look at it like this, it looks really reductive and mechanistic and linear. It looks passive in the sense that the organism is just waiting for something to happen. And it's like a stimulus response model, in which case you could say the organism is not doing anything here. It's just being pushed around by what's happening within it. It's being pushed around by its parts. Now, that's partly because of the way that we do our experiments, where we usually use really controlled environments where like the only thing that our bacterium is exposed to is this gradient of food molecules, for example. So we're isolating everything else. We're holding all the rest of the context constant, and we get this illusion of a very reductive mechanistic kind of thing. But the real world is much more complex and dynamic like that. This guy might be inside your gut, and depending on your diet and what other organisms are around and all sorts of other things, it has to integrate all of that. So when you look at the details of these pathways, they actually look more like this. There's all kinds of signals being integrated at the same time. The signal transduction pathway is much more complicated. It's affected by context like the metabolic state, the cell density, temperature of the system. And importantly, it has temporal feedback. So it keeps track of what the signal was like a second before, 5 seconds before, and then depending on whether there's an increase or decrease in the signaling, that's how it knows it's going up or down a gradient, right? So it's got short-term historicity in the system, even in the biochemistry, as well as this integration of different signals and its global state. So it's effectively the whole thing, the whole agent is actively seeking out information, and it's incorporating that and accommodating its behavior to the overall situation that it's encountering. It's a much more agentive view of things, I think, than this sort of passive, linear, reductive view. So I think some of the reasons why we can justify calling this agential is that, first of all, the meaning in the system is meaning for the organism. The organism is the locus of concern, right? That's the thing. The whole global pattern, this self-stabilizing process, is what is being maintained through time, right? The individual proteins and stuff like that, they're all in flux. They're not a locus of concern. And the meaning and value are anchored in how good that persistence happens by natural selection. So the organism is the locus of fitness, again, not its parts. And the organism acts holistically for agent level reasons, not part level reasons. It's the locus of causal power. Okay, now that's for simple critters. But of course, multicellular organisms face the same challenge, right? What's out there and what should I do about it? So they had to evolve equivalent systems in multicellular ways, both sense organs and motor effectors, muscles, but also a control system. And of course, that control system is the nervous system. But people have also tended to think about the nervous system in this really mechanistic, reductive kind of a way, where first of all, there's a tendency to focus on really highly controlled artificial situations where there's just one thing happening and you're testing an animal to see whether it's going to turn left or right in a maze or something like that, right? No, there's no context there. And it's usually repetitive, highly overtrained tasks and so on. And it's isolating synchronic causal mechanisms where you can say, I can intervene on the system in this way and cause this to happen. Therefore, that's what's normally happening, which is a kind of a short-term view of causation here, right? Again, it makes it look like an animal that's being pushed around by its parts. If you can say, well, I can activate this part of the nervous system and make an animal do something, well, then that must be what's normally going on. Its brain is making decisions. It's not doing anything. You can think about this kind of reductionism in 3 ways. This is the ordinary sort of way to think about it. This cognitive processes are reduced to neural mechanisms, and these are seen as like epiphenomena. This is the other way that I was talking about, this idea of holistic relations, this big complex interconnected web of things acting in parallel. In fact, you just reduce all of that complexity and say, no, I'm just going to look at this one little bit here, so this isolated part, and say that's the cause of what's happening. But then this is partly related to this idea where the historical contingencies are reduced to just synchronic states, right? You don't take a diachronic view. And so again, Henry and I recently published a paper that was trying to extend this idea using concepts from the philosophical literature on causation, which we think are useful to neuroscientists. So a typical view in neuroscience is this metaphor of driving activity, where you've got one neuron fires and it causes this neuron to fire by releasing neurotransmitter onto it, right? So it's again, it's this production cause, like the billiard ball hitting this kind of, like there's some sort of force driving here, and that's often how people think of it. It's often the way that, you know, experiments using things like optogenetic interventions are interpreted as forcing the animal to do a behavior. Eventually, the end of this chain is that the animal does something. Now, what we wanted to do in this paper was actually say that's completely wrong. We just have to invert the reasoning there. In fact, what each neuron is doing is interpreting its inputs according to some sort of configuration of its synapses here, some rules that are now, or criteria that are now instantiated in its wiring, where it's asking what's going on out there and what should I do about it, just like any other single cell does, like a single-celled organism does. And that's a very different view. Flipping the script like that, I think, helps to go away from an electrical engineering view of the brain to one where the brain is a meaning maker. It's a semantic engine. That's what it's trying to do all the time, is figure stuff out and make sense of what's going on in the world. So a neuron's firing depends on its inputs and on the way it's configured. It can be configured in multiple ways, where it will ignore loads of its inputs. It can filter out loads of inputs that don't fit the criteria that it has for firing. It may require, for example, 2 of its inputs to be active within 10 milliseconds of each other. Then it acts as a coincidence detector. So the configuration encodes criteria for firing. They set the sensitivity of the neuron to specific aspects of its input. And importantly, those criteria reflect the past history, but also the current state. Right? The criteria will change depending on, say, how hungry you are, or any other sort of motivational state that you have. Top-down constraints, like what goals are you pursuing at the moment? Neuromodulation, how aroused are you? What are you paying attention to? All sorts of other factors that basically reset the criteria on the fly, right? It's not just that these are set by evolution or set by your past experience. They're modulated by our top-down cognitive processes all the time. That's how we're making decisions, is by resetting those criteria. So, you know, evolutionarily in things with nervous systems, they also do these pre-wired kind of control policies. Here's an example. For, you know, in lamprey, they will respond to looming shadows, which could be a predator, with an escape response, and they'll respond to small things ahead of them, which are prey, with a hunting response. So those things are wired into the physical hardware here, but they also have control policies for how to integrate information. If there's possible predators on both sides versus if there's prey, you know, in 2 different places, they have a different strategy for resolving those kinds of scenarios. However, nervous systems really pay off when you get to the stage of evolution where there was a split between the sensory and the motor sides, with more and more internalized representation of things that are going on. So you could say that you know, some signal, you get this extraction of higher order features, like in our visual system, for example, and then the work that they're doing to, say, extract the representation of a face out in the world has to be held somewhere. It just doesn't come for free, and it has to be reported to other systems, but it doesn't have to be acted on immediately. There's a break with obligate action. And in fact, what's really useful is that it can be linked to prior knowledge. So the organism can take everything it's learned about the world and now use the information that it's getting to figure out what it should do. So what organisms like that do, they're acquiring causal models through learning. I mean, they have one to begin with from evolution, but they refine it through this kind of learning. So when they are perceiving things, they're perceiving, objects with properties, they're building categories, they're understanding the kinds of things that things are, how they relate to each other. They're learning from events, what kind of sequences and contingencies arise. They're understanding causal relations and affordances, what they can do in certain scenarios. And then they're building a self model and a world model and complicating that as they go along. So you can think about behavioral control in a moment as, perceiving what the external situation is, what my internal state is, drives, goals, and then some possible actions are suggested. They're simulated and evaluated through some kind of a competitive process. Eventually that's resolved and one action is released. So when we're acting, that's not instantaneous. Of course, most actions that we're doing take some time. They take some time to achieve the desired outcome, and that's all being assessed as we're acting. And then afterwards, if depending on whether the outcome was good or bad, our model is updated, the weights are reconfigured, that's going to change the possible actions that are suggested the next time. And we know a lot about the systems that are involved in this, systems in the cortex and the basal ganglia that are running this kind of simulation loop, biased ongoing competition. It's biased by things like internal states and motivational signals from the hypothalamus, by learning signals and reward signals from the midbrain, and eventually this loop finishes and spits out one action to be released and inhibits all of the others, and those go to motor command centers. Now, this is just for the final stage in deciding what to do, the action selection stage. But actually, most of our behavior is not just like binary, instantaneous decisions of what to do in a moment. It's ongoing behavior. We've got lots of stuff happening all the time. So we're not just making binary decisions, we're managing agendas and plans and goals and projects and commitments. Those have to be sustained through time in order to be achieved. So we have to keep running those ideas in our minds, and all of those inform action selection at any moment. So really what we have is this kind of nested, self-directed behavior, which is very hierarchical. And in fact, each of these higher levels where we have plans and policies and so on are constraining what's going on at the lower levels. And there's these equivalent loops to the action selection loop at higher levels, like with prefrontal cortex. There's a loop very much the same that's selecting goals. There's another one for selecting activities. There's another one for selecting actions and so on. And those are constraining each other as they go along. Okay. Now, that is a picture of how organisms are trying to control what they're doing and make happen what they want to happen. But there's a few sort of issues here with getting back to this question of determinacy and what the world looks like at a physical level. So again, they're trying to make happen what they want to happen, but only at the scale that they care about and can influence. They don't care what's happening at the scale of quantum events and fluctuations and so on. They don't need to control that. They couldn't anyway. What they need to control is the macroscopic goings on that within their own body, to the extent that they can then control what happens macroscopically in the world, right? They don't need to waste effort on meaningless details. And in fact, they can't know them anyway. They're making decisions under bounded rationality, right? They can't make ideal or idealized decisions with infinite information because they don't have access to it. The problem with this idea classically in the literature on free will is this idea of a luck objection. People will say, okay, well, look, maybe it's not determined by physics beforehand what's going to happen. But if you're saying that there's some randomness involved, then isn't the randomness just making the decision? Like, how is the agent really in control there if the randomness just plays out? And, I hope the first answer to that is to say the randomness is the thing that allows macroscopic control to emerge in the first place. That's the thing that allows agents and organisms to be there constraining what's happening. But in the process of an individual decision, you could still say, okay, well, if it's not fully determined, then luck is the thing that determines what happened, not the agent. And I think that that's just a wrong framing So there is randomness at play in the decision making, or you could say there's noisiness at play, right? The organisms are making decisions with noisy components, but they're still the ones making the decision, even if it might turn out multiple ways. But over the process of deliberation, it's going to turn out one way, depending on the considerations that the organism uses and so on. And sometimes there'll be very tight control over this possibility space. It will be very tightly constrained with just a little wiggle room left. Other times it will be looser control, and maybe the organism just doesn't care as much, for example, or it can't figure things out. So the crucial point, I think, is that one size doesn't fit all. There's just very different kinds of scenarios we can encounter, that any organism can encounter, that require different decision-making strategies and mechanisms. So for example, you could have a very familiar scenario, then you've got some habitual policies that you've already cached. They might be evolutionary, they might be from your own experience, and then you're acting for your settled will with good reasons, okay? And you could say this for any organism, not just for humans. In a novel scenario, well, it may be novel, but you may clearly know what to do, right? There may be still a very clear sort of idea. Like if I offered you a bowl of sand to eat or a bowl of ice cream, I think everybody would think there's a pretty clear choice there, right? So you can act with your settled will for good reasons. When it's less clear, that becomes interesting. And there's an idea of a two-stage view of decision-making, where randomness is actually a crucial part of this. So here's a situation assessment. For a familiar one, you have this habitual response. You'll assess your progress towards a goal. For a novel one, you may suggest multiple actions. That is, multiple actions may be suggested within your brain. There's some degree of randomness at play there. There's actually some degree of randomness at play all the way through here. But in the action selection mechanisms, you may choose between these things based on your reasons that you can consciously deliberate over, or that an animal can simulate and prefer. And then as you get assessment towards a goal, there can actually be an active modulation of randomness. So randomness here, the noisiness of neural circuits, is actually a resource that the organism can draw on. And it can tune it up or down with neuromodulators like noradrenaline and so on, which increase the temperature of cortical circuits in an information theoretic term, which basically increase the search space, so you can think outside the box if what you've been doing isn't working. So this randomness is just an element of normal decision making, especially under these kinds of novel scenarios, where you're still at the end of your two-stage deliberation working for your settled will based on reasons, even if you're a little less sure about them. Then there, of course, there will be arbitrary scenarios where you have no good reason, and there's very good evidence. And actually what organisms do is let the noise settle the outcome. Right? So they'll just, if they need to make a decision fast, that's the more important than deciding A or B where they don't have a good reason. Then they'll have systems that are just noisy, and they'll let that settle the outcome. And then the final version is the sort of interesting one for debates on free will, where there's a conflict and you want to know, what should I do? And then you're making a decision under uncertainty. And really the way that we think about that is not that the noisiness is making the decision, right? It's that you have some kind of a process like this. Is from a paper by Muller and Briegel, where there's a probabilistic flow from brain state to brain state, depending on links and things that it has thought of before, and little episodic memories and so on. And it could go this way and it could go that way, but whichever way, this just is the organism deliberating. And maybe it'll act at this stage, maybe it'll deliberate for longer, maybe it'll go back to the drawing board. All of that is just the mental processes of deliberating, which are probabilistic. And the organism is doing them. It's not the noise is determining the outcome. The organism is. It's just doing it in a noisy way. So we think that that's, trying to do this massive optimization problem over a hugely complex set of informational scenarios most of the time, where there's lots of conflicting goals and uncertain information. It's doing its best to settle into a new global decision state, which is basically an optimal outcome of its cognitive operations. Okay, so to summarize then, the view that I've put forth here is the idea that fundamental microscopic indeterminacy means that the future is really open, but that indeterminacy is this pervasive indefiniteness. It's not this intrusion of new events, positive random things from the outside. It's just underdetermination based on the low-level laws of physics that creates this causal slack and an opportunity for macroscopic control, which isn't some weird metaphysical alien thing. It's like absolutely commonplace. That's why my computer is doing what it's doing right now, and it's why I'm doing what I'm doing right now. So we can think of agents as macroscopic systems that do work to make themselves happen, to propagate their own pattern through time. And one good way to do that is to have control systems that allow the organism to act causally in the world in ways that will generally help them propagate their patterns through time by making happen what they want to happen at the scale that they care about without having to micromanage microscopic goings on. So I'll leave it there, and I'm going to leave some resources here that are related. I mentioned most of them, I think, along the way, and I'm very happy to take any questions.
Thank you, Kevin. We have some time. I see the sun has just come up there behind you, so
that's exactly right. Yeah, it's
you're really
just coming in.
A good morning's work. So I see one here. Can we get some mics around the room? Maybe you can. Yeah, I'll give this to Glenda, and then.
Oh, geez, I'm a giant floating head in the room.
We're used to it.
Okay.
Hello. Just a question. Early on, when you were talking about the sort of quantum indeterminacy, and then you made the movement through to sort of physical systems, and you had the solar system example. I'm just wondering, what do you think about, is there a difference between determinism and unpredictability? And then unpredictability is, like later on you talked about bounded rationality, and humans are subject to bounded rationality, and things are unpredictable, therefore. And so you talk about, well, even Newton couldn't have predicted the solar system. So that's unpredictability under bounded rationality. But this is opposed to sort of the quantum view that you wanted to put in here, which is ontological indeterminism.
Mm-hmm.
And then, so this really commits you to a view of a quantum interpretation that is ontologically indeterminate. But I don't know how then you get all the way up to the top from there. It's like a lot of the rest of the examples you use are just unpredictability. Like, for example, determinism wouldn't kill Brownian motion. Determinism wouldn't kill any of the randomness you need. And you specifically say that organisms cannot manage the quantum indeterminacy and do not need to. So why do you need this initial part? Or is it more, is it essential, or is it rhetorical, or is it?
Yeah, no, I don't think you need it necessarily. What I was trying to do was, and what we do in the paper is actually lay out a bunch of different arguments from different angles for fundamental indeterminacy at quantum levels, but all the way up to classical levels as well. And so it's definitely not just unpredictability. And there's a whole bunch of examples that I didn't have time to go into, where people have looked, at mathematical simulations, for example, of 3-body or 5-body problems where they become fundamentally indeterministic in terms of the future could go many different ways, which is basically nothing to do with whether we can predict them or not. It's just a mathematical truth of the system that those kinds of things emerge. And partly, well, I mean, it's not fully known, the relationship between these things, right? But there's an argument about infinite information. The idea that actually the equations of physics, classical physics, are deterministic only if the parameters are described by real numbers that have infinite precision. And if they're not, then the infinite precision of the outcome is not a given. So that's just an idealization of mathematics. And there's a long history of debates around what that means in terms of real physical systems. But even someone like David Hilbert, who was the biggest proponent of using infinity in mathematics, was perfectly willing to admit that it had no meaning in physical systems, that there couldn't actually be infinite precision or infinite information. And if there isn't, then what you have in any system that would show chaotic behavior, or anything that has any kind of complexity to it, like if you went into the system and you truncated the numbers, something different would happen. Well, what I'm saying is that the numbers, the universe is truncating the numbers. They're always truncated. And so multiple things could always happen. You don't have to go in and do anything to it. That's just the way physical reality is.
Does that mean I need to believe in a mathematical universe in which the laws are mathematical and so you can truncate numbers? Or because I could just commit to a continuous universe in which, well, what you're describing is actually the limits of mathematics and discretizations of the environment, the attempt to bound it in that way. Yeah.
I'm not quite following what you mean, but I also don't think I agree with it, even though I'm not 100% certain.
Yeah, I wouldn't expect so. It's like the infinitesimal. It's like, how do you define it? And can you ever really get it? And is the real number line real? Something like that. But
yeah, well, I mean, so I think part of the problem is that we've been led astray conceptually by the successes of calculus. So calculus is just super, super good for letting us work out how dynamical systems are going to evolve. And it makes this idealization of infinitesimal slices of time that have zero duration, right? So in the limit, we get dx dt, where dt is actually nothing, right? That's the limit of each little step under calculus. But of course, that's a meaningless thing. There are no time slices of zero duration, or at least time is not made up of slices of zero duration. It's made up of slices of some duration. And so there again, you have this idealization that doesn't have a physical counterpart. And in fact, you can't compress time all the way down to nothing. There's always going to be some point. So the idea that you could have an infinitely precise physical state of the world at any time t falls on two fronts. One is the infinite information front, but also it just goes down to the Heisenberg uncertainty principle when you get small enough. But the other is that there's no such thing as time t. There's always just going to be some process where things are in flux over that duration. So the precision, just has fundamental limits.
Thank you.
Hello. So I want to start by saying that I'm very sympathetic to what you said about determinism and free will. And so I was very much on board for a lot of the talk, but then suddenly I wasn't. And I guess I want to ask about this, because I think part of your argument was that there has been this kind of idealization of the way, our understanding of the physical world works, and therefore the physical world, and we shouldn't, I mean, we need this idealization for some ends, but we shouldn't, And now there's a point where where you get to something like a model of the brain, and it seems to me that now it looks like these agents, which I guess you're thinking only of human beings, they have an immense amount of control, and they have these models which are really detailed and can break down a lot of like different conceptual components, there's semantics. And I was, my tendency was just with the same attitude that you were suspicious of the idealization in these other sciences. I was just suspicious of these levels of idealization in the human brain. So it looks like, even if there were some aspect in which there is control, for example, I was quite on board on the idea that, the relation between sensory information, action, and knowledge and learning systems, that doesn't mean that we need to have, accurate, perfect models of the world to enable to work with it. A lot of it, as you said, is back in evolution in certain ways our bodies work. A lot of it malfunctions. It doesn't need to work in an integrated way. There's a lot of tension between, parts of what I think I do. So I don't know. I was just, maybe also because it was a bit fast. You didn't provide a lot of argument for all of that. But I was just stopping at. So I was happy until we got to these very big models of the brain. Well, I will be at least suspicious that we either need something like that to make sense of control and agency,
Yeah.
It looks like we're recovering everything that we thought.
Okay, I'm trying
you
to.
know, as a neuroscience, you're making this mistake of idealizing just as these other philosophers idealize physics. So.
Okay, yeah. So I think I get your meaning and what's bothering you. So I didn't mean to give the impression that I thought these models that we develop are in some way like that we know everything, or that there's no tension involved in decision making. Quite the opposite, in fact. A lot of our decision making is heuristic. It's this optimization problem under uncertainty with noisy components. And by the way, I should say I was giving examples with respect to humans, but I think this absolutely applies to any other organism as well. Just humans happen to have the widest range of behavioral flexibility and the deepest capacity for rationalization and so on. But other animals are doing this through simulation and other kinds of processes, but they're trying to do their best in the scenarios that they encounter. There isn't a right answer to be found most of the time. There's just the best that they can do, given what they know about the world. So I don't have an idealized view of what's happening in the brain. I have actually a super messy biological view of what's happening in those systems, where it's this massively parallel optimization problem that has to be solved. And that was this sort of picture that I went through a little quickly of the whole system settling into a new state by each local bit trying to satisfy the constraints that are imposed on it. And I guess in terms of decision making, what's important is that agents, and in particular agents like us, in say selecting a goal, right, deciding to do something, that sets constraints on the lower parts of the system, and then the system has to evolve to satisfy those constraints, right? So if I choose to play a round of golf, I adopt a goal, which is to hit the stupid little ball in the hole, and that has constraints on my action selection. I don't know if that helps at all, but I'm trying to dispel a view where I had a sort of deterministic view of what's going on, which isn't right.
But it seems that it wouldn't be necessary to think that there has to be, at the end, there is a controller, and now is the system makes a decision and everything else has to respond to it. It could be a more kind of interactive balance in relationship with things in the environment. And it's not like, well, the decision now has been made and now all my body's just obeying the decision that has been made. It looks to me that there's part of it, of course, that there is, but there's also back and forth.
Yeah, right? Absolutely. No, but that's all part of it, right? I mean, that's all part of the decision making. And so, I was talking about the top-down constraints. I have certain goals, but of course, like what's happening in the world right now and what my internal state is, all of that is being integrated. So this is absolutely very much an interactive kind of a thing. And I don't mean it, and apologies if I gave the impression that there's like this top-level controller pulling the levers, little homunculus in our prefrontal cortex, which is deciding what to do as the pinnacle of a hierarchy, right? That is a kind of a caricature or cartoon. And yeah, I can see why you would have gotten that impression from the way I presented it. I don't believe that. It's much more interactive, up and down, lateral, global decision-making process. That's why I would insist that it's agential and not just mechanistic.
I think we have time for one more question, maybe Moritz.
Thank you very much for that interesting talk. I'm gonna try to keep it short. I'm very sympathetic to I saw you're avoiding emergence as much as possible. And as philosopher Paul Humphreys in his big book on emergence said that emergence only makes sense from a reductionist standpoint, because you need something that bottom up emerges. If you take a holistic perspective or some whatever top down perspective you want to take, it doesn't make any sense. But then you kind of end up with this two levels that you have top down and bottom up approaches. And my question in the end is like, can we then even formulate like a unified model of agency, or should we accept that there are these different levels of description that we cannot get rid of?
Yeah, there's different things going on. I think it depends what question you're asking, right? Whether anything rides on that. If you want to know how are we choosing a goal and how a goal influences the actions that we do, then thinking of that in a top-down kind of a way becomes useful, but that's not an ontologically top-down way, right? That's just the system is organized with a kind of a hierarchy of decision making, where I mean the hierarchy in that sense is because it's nested over different timescales, right? So you have decisions like adopting a goal that's over a long time scale that constrains what happens over a shorter time scale. So, you know, when I say things are transcendent, and we can think about them as agents and holistic entities with causal powers unto themselves, I don't mean they're not affected by what's going on in their physical parts. So if, for example, you want to understand a neurological situation or a psychiatric condition, then you need to know how what's going on at the parts bubbles up, as it were, or affects what's going on at the higher levels. So in that kind of a scenario, it becomes important to be able to trace that thread. In other scenarios, if you're talking about cognitive science and so on, you can do cognitive science, right? You can do psychology as a science unto itself without constantly thinking that you need to be doing some neuroscience underneath it to validate it with mechanisms, right? So I think it's right to say that we have some levels that have their own causal dynamics that we can investigate in that way. And then whether we need to consider the relationship between those just, I think, depends on the question that we're asking. I don't know if that's a satisfying answer at all.
Yes, I agree. Thank you very much.
Okay, thanks.
Kevin, I know we've pushed over time, but do you have a few more minutes? I think there's a few more questions in the audience.
Yeah, sure, yeah.
So
yeah. I'm awake now, so.
We see the sun is really knocking on
It's
your
really
door
coming
now.
in. I might actually just, while that question's coming, I'm just going to move my, oh, you know what? I'll do this. Yeah, that's better.
Thank you so much for the talk. I take it the account on offer is still a fully causal story, compatible with a naturalistic explanation. And I just wanted to ask if you could say more about how reasons fit into that. Like, for example, like philosophers like to talk about the logical space of reasons and how it's difficult to naturalize that.
Well, yes. So first of all, yes, absolutely, all naturalistic. There's nothing mystical at play here. You know, if I'm deciding to do something, we can couch that in perfectly reasonable terms. So, yeah, if I'd had longer, there was a whole section on reasons and cognition and the idea that actually, you know, there's a view that some people have where all of the cognitive processes that we have, like beliefs and desires and goals and different cognitive states that psychologists and cognitive scientists talk about, are actually just neural states, and that all the causation in the system is by patterns of neural activity driving other patterns of neural activity. And I think you can invert that relationship, causally speaking, and you should. In fact, you can say that the only reason that neural patterns have the causal influence that they have within the system is because they mean something, because they have come to mean something to the organism in its interactions with the world and the way it grounds representations and builds up these models, so that it's really operating over meaningful patterns. And the criteria that one, say, neural population has in responding to another neural population activity is set by it looking for a pattern that means A versus a pattern that means B. And that's multiply realizable. So there's loads of possible microstates of one neural population that can all be interpreted as an equivalence class by another population that's monitoring its activity. And I mean, you guys are doing that right now because you're all interpreting the patterns in your visual cortices that are representing my face as still being me, despite the fact that I'm turning all around the place, right? So, so what's important there is that the low-level details don't matter. They're actually filtered out. They're arbitrary and incidental. And what really matters is the patterns and what those patterns mean, so that you can flip the script there, as it were, and say actually the supervenience relationship in causal terms is the opposite from what people have usually thought in neuroscience, this reductive kind of view. And it's a way to defend the idea that the brain is a semantic engine. It's not just an electrical engineering device, right? So in that context, with that kind of a view, then having a reason to do A versus B can be cashed out in terms of setting these criteria for action, depending on what information you then get. And that view of criterial causation, I think, becomes a really powerful way to ground a naturalistic view of cognition that rides on top of some neural instantiations at any moment. It does depend on some particular instantiation. It's just that the details of that are not where the causal sensitivity lies within the system. And does that come some way at least to satisfying?
Yeah. Thank you so much.
Okay.
Was there any other questions? Conrad?
Thank you. Thank you for the talk. It was wonderful. So it's a strange question, and this is what happens when you give people additional time. Let me put it this way. The question is inspired by this famous dictum by Umberto Maturana, that everything said is said by an observer. So in this case, you said that each organism or each cognizer, if it's not the same, asks, even the simplest cognizer, asks a question like, what is happening out there? And then the second question is, what am I supposed to do with it? So this is like, this is the way in which we see a certain agent and a situation around this agent. And then we can draw a picture. Oh, here is this agent, and here is the situation around the agent, and even a very simple agent like a bacteria. But this is not the way in which the bacterium sees its own situation, likely, let's say. So if I am the simplest possible agent, let's say, perhaps the first question that I should ask is, or the first thing that I should do is to realize that there is any out there, that the world is not just me, but there is such a thing as out there. And so to come up with the idea that there is something outside of my boundary, that the stimuli are not just happening on my surface, but they are like coming from somewhere. And so the strange question is this realization part of the story you are telling? Is this a kind of agency as well, perhaps? Is there any control in it? Do I have any control on how I realize that there is any out there, let's say? And finally, is there any freedom or indeterminacy in this realization? Thank you.
Yeah, super interesting question. I would say that you don't need to, the organism doesn't need to realize anything. It just needs to do appropriate things. It needs an as-if realization, what Dennett has called competence without comprehension at these lowest levels. It doesn't even need really apprehension of a signal, right? So you've got, any living system has a boundary with the world. There is, in physical terms, a real division between the organism and the environment. That's not just an imagined thing, and it can be formalized in all kinds of scenarios. You can use the free energy principle if you like. There's all, but autopoietic kind of persistence and so on. All of that fits with this idea that there's a set of processes that are ongoing, that are a thermodynamic unit, that are trying to keep going as an entity, as a whole regime of processes that's different from the maelstrom outside of it. Right? And in order to keep going, it just is the case that it pays to be able to have some information about what's out in the world, right? Because you might exhaust your food source, because there might be too much waste products from metabolism that you then have to move away from, because you might be so successful at reproducing that the world becomes too crowded with more you, right? So all of those things just make it valuable evolutionarily for organisms that are trying to persist to have some information about what's going on out in the world, while also remaining causally insulated from it, right? So they don't want to just open it to everything. So instead they develop these specialized receptors that are not passing physical causal momentum or energy. They're just detecting information and conveying it to the inside of the cell, where again, there will be selection for appropriate processes, where in that case, the meaning of what's happening, it's not that the signal is apprehended by the system and internally represented and then used to decide what to do. It's just pragmatically linked directly to a sensory motor kind of contingency, even if there can be some contextual evaluation sort of modification. So you can have all of that without having something that you're thinking is cognizing or realizing using those kinds of terms, even though eventually over evolution, it does get to that point where actually it does become an internalized representation that reflects what we think of usually as cognition or cogitation, real sort of representational symbolic thought. But I see that as very much as a continuum that starts with this kind of pragmatic control policies and eventually gets to things that have real semantic, a semantic system in which they can operate over meaningful symbols.
Push it further, but we have no time for that. And
yeah, perhaps we can leave it there. Say thank you very much, Kevin.
Yeah, absolutely. My pleasure. Thanks for your attention. Thanks for your questions, and thanks for the invitation. I'm sorry again that I couldn't be there, but next time maybe.
Yeah. The only shortcoming is that you couldn't be here, and I think your spirit will persist throughout the week as we engage with your ideas. And
well, thanks. I appreciate that.
All right. Thanks, Kevin.
Thank you.
See you soon.
Bye all.
Bye. Thanks, everyone. We're getting